Hello everyone. Today I want to recall first what we did in our last lecture. Okay, so we studied about existence and uniqueness theorem. What this theorem says? It says that if you're given an IVP, y prime equals fxy with an initial condition yx naught equals y naught. That means that x naught y becomes y naught. That means this point x naught y naught. And you find out that the fxy, this function, is continuous around some region of this point. Okay, so we are calling this region, that region, as R. So if fxy comes out to be continuous around x naught y naught, and also its partial derivative with respect to y is continuous on that same region, then we can conclude that our IVP will have a unique solution. Okay. Now I tried explaining you this using a graph, right? So suppose this is our fxy, okay, this function, and x naught y naught is here, okay. So we'll take a region around this point and we'll call it as R, and we'll check the behavior of our fxy and its partial derivative with respect to y in this region. If these both comes out to be continuous in this region, then we can say that our IVP has a unique solution in some interval. Okay. Now I also told you that there exist some functions that lack continuous partial derivatives. Right? For example, if you are given such an IVP, y prime equals root y. Okay, so here fxy is this, right? And your initial condition is y0 is 0. That means at x equal to 0, y is also 0. That means this point 0 comma 0. That means we'll check the behavior of our fxy around this point, right? Now this is our fxy, and if we try calculating its partial derivative with respect to y, we'll get 1 over 2 root y, that you know is not defined at y equal to 0. And when it is not defined at y equal to 0, then how will you uh, conclude that if it is continuous at y equal to 0 or not? And we need to know this, right? We need to know if it is continuous at y equal to 0 or not. Only then we can conclude that if our IVP has a unique solution or not. But what can we do? So for that, we'll study another term, which is Lipschitz condition. Okay, so this condition will replace our second condition in this case. This is our second condition here. This, that the partial derivative should be continuous on R. We'll use a Lipschitz condition in place of this condition if we are given such an initial value problem where the partial derivative does not exist at some point, right? So we'll use a Lipschitz condition at that, in that case. What this Lipschitz condition says? It says that mod of fx comma y1 minus fx comma y2 should come out to be less than equal to n mod y1 minus y2, where n is a Lipschitz constant. Okay, so we'll try using this condition in a problem. So if you're given a problem, discuss the nature of solutions of the initial value problem. Y prime equals root mod of y, and the initial condition is y0 is 0. Okay, and you have to check it on the rectangle mod x less than equal to 1 and mod y less than equal to 1. Then how will you do that? So the solution says the function fxy. Here you know that this is our IVP and this is our fxy, right? So here fxy is given as under root mod of y, that you know is continuous for all values of y. Now the second condition is Lipschitz condition, right? The first condition is satisfied. fxy is continuous. Okay. Now the second condition, we have to satisfy the Lipschitz condition, right? So we are calculating this first. Now this is fx comma y1 minus fx comma y2. That means we are calculating f at two different points. Now if I take y1 as 0 and y2 as greater than 0, because we can take y, we can take any value for y, but it should be less than equal to 1. Okay, so we are taking y1 equal to 0 and y2 as greater than 0. Okay, so if we try calculating f at x comma y1, that we are taking as 0, so fx comma 0, fx comma 0 will become root 0, right? That means 0 again. So fx comma y1 or fx comma 0 will come out to be 0. Now minus fx comma y2. y2 is greater than 0. So we are putting y2. Okay, we are using y2 in its place, but we are assuming that it is greater than 0. Okay, so fx comma y2 will be equal to under root mod of y2, right? So here you can see that this, because fx comma y1 is 0, okay, and fx comma y2 is root mod y2. So root mod y2 minus 0 will become root mod y2. Okay. Now this this right hand side, this mod y1 minus y2. Now you know that y1 is 0, so 0 minus y2 will become y2, right? So y2 minus y1 is y2 again. Now we have to make this over this less than equal to some n. Okay, Lipschitz constant. Now you know that this over this comes out to be 1 over root y2, and now we have to make this less than equal to some n, some Lipschitz constant. Okay. Now you know that this term can be made as large as we please by choosing the sufficiently small values of y2, right? Therefore, there exists no n independent of x comma y such that the Lipschitz condition gets satisfied. Okay, so here you can see that we cannot find any n that is greater than equal to this term, right? And that n should be independent of x and y. So we cannot find any such n. That means the Lipschitz condition is not satisfied in this case. Okay. And you also know that if we try solving that initial value problem, we'll get the solution as yx equal to x square over 4, right? And also, if you look at the problem given to us and you try putting y equal to 0, then dy by dx will also become 0, right? So it is satisfying our differential equation. That means y equal to 0 is also a solution of this differential equation. Okay, so you can see that the Lipschitz condition is not satisfied for this problem, right? And as you can see, we did not get a unique solution, right? We were able to find two solutions. Okay, that's all for today. Thanks for watching.